Oh, you're recording a
Recording
German
session?
class?
Oh, no. What page are you on?
All right, page 130, title is Inverse Relations and Functions. All right, we have some definition-y kind of stuff to do here at the beginning. An inverse relation is when you have an ordered pair such as A comma B and you flip-flop each term to get B comma A. So inverse, kind of like, you know, when I ask you what's the inverse of multiplication, you say division. What's the inverse of addition? You say subtraction. A lot of people say opposite, but opposite is not the technical word, okay? So inverse basically is kind of like the opposite. So instead of A comma B, it would be B comma A. Or instead of X comma Y, it would be Y comma X. You just switch their places, all right? If both the relation in parentheses ordered pair means the same thing as a relation, and its inverse are both functions comma, they are considered inverse functions. The inverse of a function may or may not be a function. Now, y'all may remember, hopefully you remember because we just learned about graphing rational functions, what an inverse is. Or, I'm sorry, not what an inverse is, but what a function is, right? Remember, it has to be able to pass the vertical line test. Basically meaning you can't have any two x values that are the same, right? That's a function. So when I'm giving you a relation, which a relation is basically ordered pairs, and we find the inverse of them, the inverse may be a function, it may not be a function, okay? But if the original relation that I give you is a function, and then we find the inverse and it is also a function, then we say that they are considered inverse functions, which is what I wrote here. But the inverse might not be a function. It might be a function. It might not be a function. Remember, to be a function, the domain which the domain is your x values, cannot repeat. Also, remember, we call it, it's got to pass the vertical line test, which it will if your domain does not repeat. For example, is this a function or not a function? Function. Function or not a function? Not a function. Definitely fails the vertical line test, right? Function, not a function. Function. That is a parabola, which means it was a quadratic function, right? That says function. It's hard to read, but it says function. Is this a function or not a function? Not a function. Function, not a function. Function. Okay? Again, think about the vertical line test, or again, if I had this heart on a graph, this x value and this x value would be the same of those ordered pairs, right? So they can't have repeating domains, because that means they'd have the same x value, or again, vertical line test. So y'all remember what a function is. We're good with that. All right, I'm going to show you about relations and their inverse in a couple of different ways. The first way I'm going to show you is with a mapping diagram. Y'all remember seeing these mapping diagrams? No, never? Okay, domain means what? Your x values. Range means what? Yeah, we were making graphs. So if I asked for the ordered pair that had the x value of 1.2, what do you think its y value would be? 1. What about 1.4? 1. What about 1.6?
So that's not a function then?
Well, it's a mapping diagram. It's just a way to write ordered pairs. And then 1.9, comma 2. Does this represent a function or not a function?
Function.
Function. Was that what you were asking, Houston?
Yes.
Oh, sorry. So this is a function. It's okay if your range repeats, because that would be on the same horizontal line. That doesn't matter. It's not okay if your domain repeats. Okay, if I said, all right, well, I want you to give me the inverse of relation R. Inverse just means that now my domain will become my range, and my range will become my domain. I'm not going to change the heading though.
And then it won't be a function.
right. So now instead of my range being 1 and 2, my domain will be, 1 and 2. And my range will be 1.2, 1.4, 1.6, 1.9. We'll still pair the same numbers together. Bless you.
Is it still a function?
I made a mistake. Oh, where's my whiteout? This one meant to go to 1.2 and 1.4. I drew them both to the same thing.
Does it still count as a function?
We're gonna see. You tell me. Does anybody have any whiteout handy?
I do.
Thank you very much. Some fancy. Pause. Okay, so I fixed my mistake. Those of you watching at home. Did I do it right?
Yes.
Okay. Is this going to be a function?
Yeah.
No, it's not, because if I write out my ordered pairs, I'll have an ordered pair of 1, 1.2, 1, 1.4. Right there, I already have repeating domains, right? So right there, it can't be a function. But I'm going to keep going. I'll have an ordered pair of 2, 1.6 and 2, 1.9. And I have 2 more repeating domains. You only have to have repeating domains one time for it to not be a function. But it's got it twice. So regardless, it's not a function. So the initial relation was a function. Its inverse is not a function. So in the second arrow at the top of this page, it said if both the relation and its inverse are both functions, then they are considered inverse functions. Are these inverse functions?
No.
No. Everybody good? All right, page 131. What is the inverse of relation S? All right, so this time I'm going to give you the relation in a table of values. So I have 0, comma, -1, 2, comma, 0, 3, comma, 2, and 4, comma, 3 make up relation S. So is relation S a function or not a function?
Yes.
Yes, it's a function. So the inverse of relation S,
Is a function.
is it now?
Yes.
So instead of 0, comma, -1, the inverse of that would be what? -1, 0. Instead of 2, comma, 0, we would have 0, comma, 2. Instead of 3, comma, 2, 2, comma, 3. Instead of 4, comma, 3, 3, comma, 4. So is the inverse of relation S a function?
Yes.
Yes. So since the relation and its inverse are both functions, then we call this inverse functions, okay? Now let me show you what they would look like on a graph. And then we'll actually get to solving some equations, okay? But I really like to go through the beginning of what is an inverse actually, what does it mean? Because if we just went straight to the equations and I said, okay, this is how you find the inverse, then that's never going to mean anything to you. Like, okay, what does the inverse actually mean? So we're going to graph relation S and the inverse of relation S. And I am going to put those on two different graphs. So my first one will be for relation S, which has an ordered pair at 0, comma, -1, at 2, comma, 0, at 3, comma, 2, and at 4, comma, 3. And that is relation S. So looking at it graphically, does it pass the vertical line test?
Yes.
Why, yes it does. There is not any place on this graph where any of the ordered pairs would touch my vertical line more than once, right? So function. Inverse of the relation S, we already said it was not. Let's just graph it and see what the graph looks like. I've got an ordered pair at -1, comma, 0, at 0, comma, 2, at 2, comma, 3, and at 3, comma, 4. And as you can see, the inverse of relation S also passes the vertical line test. Wasn't that awesome? I know. Okay, so now let's get down to some algebra stuff. Let's do some equations where I give you a function and we find the inverse of that function. Or I give you an equation and we find the inverse of that equation. So page 132. So my example, the directions say, what is the inverse for the relation described? And y equals x squared minus 1 is my problem. Do y'all remember what shape that's going to make?
Parabola.
It's a parabola, right? Is a parabola a function?
Yeah.
Yeah. So just because this doesn't say f of x doesn't mean that it's not a function. But if you do see f of x, that means it is a function, okay? But we know that's going to be a parabola, and parabola is always a function. So what we do is, remember what we did before when you were given a table of values or a mapping diagram. To find the inverse, what was your domain became your range, and what was your range became your y, right? You flipped your x and your y. Am I right? So that's the same thing we're going to do in the equation. We're going to flip the x and the y. Of course, we're going to write that down. Since we flip-flop, and I'm putting that in quotation marks because flip-flop's not exactly a true math word. Since we flip-flop the x and y, to find the inverse of a relation, we will do the same thing to find the inverse of an equation. And the equation is a relation written as an equation. So y equals x squared minus 1. That will become x equals y squared minus 1. Do you think that's all we do? No. That's the first thing we do. We flip-flop the x and the y, okay? Once we do that, then we have to get y all by itself again, okay? So you flip-flop the x and the y, and then you isolate the y. So the y was started out as being isolated. Now it's not. Now the x is isolated, right? So we just got to get it back into the form that has y all by itself. And these are all going to be different. So in this example, what do you think I'm going to do to start trying to get y by itself? Add 1 to both sides. So I have x plus 1 equals y squared. We know what to do if something's being squared. We're going to square root. Now, when we do the square root, we take the positive and the negative square root of the other side, right? And that's going to be important when it comes to determining if the inverse is a function or not. So, can we take the square root of x plus 1?
No.
No, if it was x plus 1 quantity squared, we could, right? But we can't. Can we take the square root of y squared? Yeah. So I'm just going to rewrite that with a y on the left. So y equals plus or minus the square root of x plus 1. There's nothing we can do with that.
Is that solved?
That's we've gotten the y by itself, and we can't do anything else. Okay? Nothing else we can do. Because if we get rid of the radical, we're going to have to raise both sides to the, we'll square both sides, and that's going to end up getting y squared again, and we want y to be by itself. Okay?
It's because there's too many variables.
Yeah, we have two variables here, where before we just had one. In the last homework we did, we just had one variable, right? And this has two variables. So if we want to get y isolated, that's all we can do. Otherwise, we start putting stuff back with y. Okay, so we haven't learned how to graph radicals yet, right? We do know how to graph parabolas, quadratics. We're just going to kind of do a quick sketch. We're going to plug in some ordered pairs. We're not going to go through the let's find the vertex and all that kind of stuff, but that'll kind of help us remember. I want to graph y equals x squared minus 1, and then I want to graph y equals plus or minus the square root of x plus 1, okay? Just quick sketches of the graphs. So for y equals x squared minus 1, let's make a little table of values. I'll try to do that down here. I'm going to pick some negatives and positives. They may be good numbers, they may not, but it's a good starting place. And we'll probably do the math on this in our head, okay? So if x is negative 2, that means negative 2 quantity squared is what? 4. And 4 minus 1 is? 3. Plug in negative 1. Negative 1 quantity squared is?
4.
And 1 minus 1 is?
0.
Plug in a 0. 0 squared is? And 0 minus 1 is? Plug in a 1. 1 squared is? 1 minus 1 is? Plug in a 2. 2 squared is?
4.
4 minus 1 is?
2.
Okay, let's graph this. And we already knew that parabola was going to open up. We knew it wasn't going to be a stretch or a compression because A was 1, right? So we know from the vertex we go up 1, right 1, and up 4, right 2. That would give us some points. Same thing as up 1, left 1, up 4, left 2. We knew basically the parent function was just going to shift down because we remember our transformation rules, don't we?
Yeah.
Or kind of maybe when I bring it up a little bit. So, is that a function? Yeah, which we knew it was going to be. It's a function.
The inverse is
Is the inverse a function?
no.
All right, let's check it out. Sorry, that was weird.
Is this like complicated?
Huh?
This is kind of complicated.
Okay, so this is, I don't think it is. Mm-mm. So I'm going to use the same x and y's.
John should take complicated.
I'm going to use the same values that I did over here. right, if I plug in a negative 2, what's negative 2 plus 1?
-1.
Negative 1. Square root of negative 1 is going to be an imaginary number, right?
Yeah.
Is that going to help us here?
No.
No. Okay, so that's not going to work out. If I plug in negative 1 plus 1 is 0. What's the square root of 0? 0. Positive or negative, right? It's still 0. Because you can't have a positive and negative 0. If I plug in a 0, 0 plus 1 is 1. Square root of 1 is, so that'd be positive 1 or negative 1, right? So when x is 0, y is 1 or negative 1, right? Because of the positive negative. If I plug in 1, 1 plus 1 is 2. The square root of 2, this one's going to be a pain. I mean, not that we can't do it. So square root of 2. Can you ever find my square root button on this calculator?
It's above the
0.
2 spaces above the 9.
Oh, thank you. 2 square root. Approximately 1.4. And it's going to be positive or negative 1.4. Sorry, I can't see my paper. If I plug in a 2, 2 plus 1 is 3. And it's going to be positive negative square root of 3. So 1.7 and negative 1.7. Let's make this a perfect square. If we plugged in a 3, 3 plus 1 is 4. So the square root of that would be positive 2 or negative 2. Is this going to be a function? No, because a lot of times when we plugged in a value for x, we got two different values for y because of the positive and negative thing with the square root. See what I'm saying? Okay, so I didn't use that one. When x was negative 1, y was 0. When x was 1, y was 1.4, and also negative 1.4. When x was 2, y was 1.7, and also negative 1.7. When x was 3, y was 2, and also negative 2. I didn't do good points here because, well, I'm doing a hand-drawn graph. But this should look like, kind of like a parabola on its side. But we don't call it a parabola if it's on its side, okay? Yes?
I thought it was supposed to be the inverse. Why do we still have like the x values the same on each side?
Well, okay, so I was going to point that out, but good question. So I picked, what I did when I found these ordered pairs over here, I just found the same x values that I did for my other one, right, when I was graphing. What I could have done was, I could have said over here, okay, well, if this is the inverse, then I should have the ordered pair, instead of negative 2, comma 3, I should have 3, comma negative 2. Did I? Mm-hmm. Instead of negative 1, comma 0, I should have 0, negative 1. Did I? Yes. Instead of 0, negative 1, I should have negative 1, 0. I did. Instead of 1, 0, I should have 0, 1. I did. Instead of 2, comma 3, I should have 3, comma 2. I did. So what we could have done was just, if we knew the ordered pairs for our quadratic, we could have flip-flopped those, and then we wouldn't have had to have all these like weird decimals and stuff. It would have been a little bit easier. But in the end, not knowing that and just going through the math, we ended up having the inverse ordered pairs, right? Okay, so is my inverse a function? Not a function. Notice how quadratic is always going to go up or down. It's never going to go sideways, right? We knew this minus 1 would make the parent function drop down 1 unit. Everything would. Notice what happened here. The inverse of the quadratic, put it on its side, and it shifted over. It shifted it to the left 1. Okay? And it's because of that plus 1. Yeah. So you'll get to kind of notice. But if you can't remember, like, I don't remember what the graph of a when you have a radical square root, I don't remember what that looks like. Pick some ordered pairs, plug it in, just like any other graph that you can't remember how to graph. You know what I mean? May take you longer, but it works. Pick some values for x, plug it in, get your values for y. I'm not going to do that for all of them. I just want you visually, on some of them, I will do that. Page 133.
Where's 132 right now? It's 133 right now.
Weird. Meant to be.
Last page.
Find the inverse. We'll see. And my problem is y equals 2x plus 8. What would that be the graph of?
Linear.
It's a linear graph, right? Its degree is 1, x's exponent is 1, so it's linear. Is that a function? Yeah, it's a function. Only kind of line that's not a function is a vertical line, but any other line is going to be a function, right? Okay, so we don't even need to draw that. We know it's going to be a function. But if we were going to draw it, what would my y-intercept be? 8, and what would my slope be? 2 over 1, and it's positive, right? Okay, we're going to find the inverse. So the first thing we do is we just flip-flop the x and the y. Or let's say switch x and y. Once we do that, we do whatever we have to do to isolate the y. So what? Subtract 8 from both sides. So x minus 8 equals 2y. Divide everything by 2. I like to put my y on the left side. So y equals, instead of x over 2, that's going to be my slope. I would write that as 1/2 x. You can write x over 2. It means the same thing. It's just not as pretty to me. Right, because there's a 1 there. And then the x we can put right next to the fraction. And then minus 8/2 is the same thing as minus 4. Well, what kind of function is that? It's linear also. Is that also going to be a function? Yeah, so these are inverse functions because they're both functions. How about this? Y equals, open parentheses, 3x minus 4, quantity squared. What am I going to do first? Switch the x and the y. So that'll be x equals 3y minus 4, quantity squared.
Square root it.
Okay, don't square root it before you flip-flop them. It's always flip-flop first, okay? So flip-flop, I want to get y by itself. It's being squared, so I'm going to take the square root of both sides. So the side that I'm not trying to isolate, I'll take the positive and negative square root of that side.
Wouldn't just be 3y minus 4.
Right. So on the right side, we'll have 3y minus 4. Can I take the positive and negative square root of x?
Yes.
I can? No. It's just positive, negative square root of x, right? Add 4 to both sides. Now, can I add 4 to that x under the radical?
No.
No. So I would write that as 4 plus or minus the square root of x equals 3y. Divide by 3.
Shouldn't the x go first because it's standing form?
Not because there's a radical. It doesn't. It's okay.
Unless it's also
So y equals, can I do any simplifying with this? No. So 4 plus or minus square root of x over 3. Now, even if I did not graph this, could I tell if it's a function or not?
Yeah.
I can tell. Is it a function? No. If I have a domain of 4, if I plug in a 4 for x, the square root of 4 is going to be positive 2 or negative 2, right? So 4 plus 2 divided by 3 is going to give me a different y than 4 minus 3 divided by 2. So I can have two x's, or each x can have a different y. So not a function. It's going to be another one of those sideways looking parabolas. Square root, we have a variable under the square root, that's what kind of equation it's going to give you. But this, what we started with, would have been a function because our x is squared. That would have been, if we would have graphed that, it would have been a parabola because x is being squared. Let's try another one. Y equals, open parentheses, 1 minus 2x quantity squared, and then we got a plus 5 on the outside. What do we do? Switch my x and my y. So x equals 1 minus 2y quantity squared plus 5.
Go ahead and subtract the 5 before you square it, or you have to.
Oh yeah, you want to go ahead and subtract 5. You want to isolate the parentheses. So we have x minus 5 equals, open parentheses, 1 minus 2y quantity squared. We're going to what?
Square root both sides.
Square root both sides. Make sure you take the positive and negative square root of the side that you're not trying to, that does not contain the y. Can I take the square root of x minus 5?
No.
No. So I'll leave that as positive, negative. Square root of x minus 5 equals the square root of 1 minus 2y quantity squared. It's 1 minus 2y.
You add 1.
I will
That's one.
subtract 1, and I cannot subtract it from under that radical. So I'll just write minus 1 plus or minus the square root of x minus 5 equals negative 2y.
You divide -2.
Divide by negative 2. Now I can write one big negative 2 on the bottom, but since you can't have a negative in the denominator, I'm going to separate it out to make it easier for me to see what my sign should be. So I'm going to write my y first. Okay, this negative 1 divided by negative 2 will become a positive 1 divided by a positive 2, right? Plus or minus. Now this negative 2, since this is plus or minus, positive divided by negative is a negative, negative divided by negative is a positive, so the positive negative will suffice because you already have both signs there. Now, since that still has the same denominator, could we rewrite it?
Yes.
Yes. Is that going to be a function?
No.
No, because whatever I plug in for x, and I take the square root, I'm going to get the positive and the negative when I simplify for y, right? So not a function. So are you seeing sometimes that when you take the inverse, you're going to have a function, and sometimes when you take the inverse, you're not going to have a function? Yes, Miss Freely, we are seeing that. Oh, good. I was hoping so. I want to show you one more thing. Everybody good with this?
Yep.
Page 134. The inverse of function f is denoted by, it looks like f raised to the negative 1 is what it looks like, but you read it as the inverse of f. So when you're talking about inverses, you wouldn't say, oh, f to the negative 1, it's the inverse of f is what it means. Or you could say f inverse. But f to the negative 1 is not how you say it when you're talking about inverses. The notation f of x is used for functions. Sorry, that's a crazy looking U. But the relation inverse of f may not be a function. And you can't use function notation if a relation is not a function. And that's important because, like, in the problems that I've given you so far, it's been like y equals x squared minus 1 or whatever. But if it gives you the notation f of x equals x squared minus 1, well, when you do the inverse, you might be tempted to write f of x equals positive negative square root of whatever it was, x squared plus 1. But if it's not a function, you cannot use f of x because f of x is saying it is a function, okay? So a lot of times, if they give the problem to you in function notation, f of x, when you find the inverse, instead of writing f of x, write inverse of f. Okay? If it's g of x equals, write inverse of g. If it's h of x equals, write inverse of h. So what I'm talking about is, in this example, they're going to give it to me written in function notation. And you're thinking, well, I thought that square root thing was a sideways parabola. Well, the difference on this is, yes, there is a square root, but it doesn't have the positive negative in front of it. So if that positive negative is not there, if I just were to graph that, see if I can do this real quick for us. If I were just to graph the square root of x minus 2, you just have that top part, okay? If I did positive plus or minus square root of x plus minus 2, it would be the sideways looking parabola. All right, so that is a function. Because when you graph it, and that came up on 2, it was just this top part. So that is a function. So that's why it can be okay to say f of x. All right, so, but when I switch my x and my y, I'm not going to rewrite this with f of x. So I like to rewrite it first and put an x in there in place of the f of x. But a lot of times when kids do this, they think they already switched it. Have I already flip-flopped them? No, I just changed out the f of x for a y. So I did get confused. So when I flip-flop it, it'll be x equals the square root of y minus 2. Now what am I going to do? Not square root both sides. Square both sides. So x squared is just going to be x squared equals, what's square root of y minus 2 quantity squared? Whoops.
Well, it's just-
Y minus 2. Now what? So y equals x squared plus 2. Since they gave it to you in function notation, though, you're probably not going to see it written as y equals. You'll see inverse of f equals x squared plus 2. What kind of, if I graph that, what am I going to get? A parabola, right? Is that a function? Yeah, parabolas are functions always. This was a function. So since they were both functions, their original relation and its inverse, this would be considered, they would be inverse functions. All right, we cool? Do we have a question? All right, anybody still writing?